generators and motors are a great application of Faraday's law. So for an AC generator, there's a really simple setup. You have a coil, here it's in this region between two permanent magnets. So we've got the poles of the north and south pole of these two permanent magnets, and we rotate the coil as shown right here. Right, so as this coil is rotating, your flux is changing, right? Your flux changes BA cosine theta. So as the normal direction of our loop rotates around in that magnetic field, that theta is what's changing. So you're going to get an induced EMF in our coil there. So this induced EMF is going to be negative N. So if we have more than one coil, d phi dt. So in this case, it's negative NBA because the area of the coil is not changing, the magnetic field is not changing, it's just the angle that's changing. So the time derivative of cosine theta. So we want to know how fast is theta changing, right? So if you remember your angular velocity equation, your angular velocity is just how many radians per second, right? How fast are you going around in a circle? And you can even talk about how long does it take you to go around in a circle? Where did you start? What's your velocity? So this kind of looks like our linear velocity equation, but it's using radians and angular velocity and angular position for our rotational motion equations. So if we just choose a region where, or choose a start of our time where theta 0 equals 0, we can just say theta equals omega t, and omega equals theta divided by t pretty easily. So if we do that, our induced EMF is going to be negative NBA, so N number of loops, B the magnetic field that's caused by those permanent magnets, A the area of our loops, and then the time derivative of cosine omega t, right? So that's where this equation above comes in. And then when we take that time derivative, we get a negative sign, so the negatives cancel out, and we get the sinusoidal function, NBA omega sine omega t. So that sinusoidal function, that omega t, tells you how fast we repeat. So this is one wavelength of our sinusoidal motion. The time it takes to repeat is given by that omega t. And then, let's see, our maximum value here, well, the maximum of sine function is going to be 1, so that maximum value is going to, hang on. So our maximum value, we can get our pen to work, is going to be that N number of turns of wire that's rotating through this field, the strength of our permanent field B, the area of our wires, and how fast we're going. So remember again that EMF depends on how fast our flux is changing as well. So that's where the omega comes in, and that's our maximum EMF here in our picture, right? And I've already said this is one wavelength, so that's one time to repeat. You can figure out that the sine function repeats every 2 pi, and so if the sine function repeats every 2 pi, you can figure out the relationship between omega and how fast our AC generator is repeating, or the frequency of our AC generator, right? So omega is related to frequency by 2 pi times our frequency. Okay, so that's our AC motor, right? Our alternating current, which is related to our alternating EMF. The next thing would be how a DC generator works. So a DC generator is a little more complicated. You actually have, so if you hear you have slip rings that are just completed rings. If you look at our DC generator, you see these rings have gaps in them. So those are called commutators. So they just only take the positive waveform. So you can see if you compare this to the previous slide, it's like you've taken this negative waveform and flipped it to the positive axis. That's what the commutator does. And then for our DC generator, you would actually smooth this out with some capacitors in the circuit so that you, wow, that's a terrible handwriting. Sorry about that, guys. So when you smooth this out with some capacitors, you get something that is more like that flat line that we've come to expect. Right, so that flat line 4 volts or whatever the heck you tell your DC generator to do. So that's a little more complicated for our DC generators. So the last application in this chapter is about eddy currents. So eddy currents, eddies, if you think about it, they're the little whirlpools and streams. So there are currents that are like little whirlpools in a sheet of conductor. One demonstration for this is that you take a conductive material and you swing it back and forth between a horseshoe magnet, as is shown on the left-hand side of this plate. So as that conductive piece of metal enters that region, you're going to induce currents in the material, right? So even without, you know, a wire, just having a conductive material, you induce currents in different directions. That's shown by the maroon arrows here in the picture. So as we enter or leave the region where there's a magnetic field, there are going to be currents induced that resist that change. So again, because this electric field that is producing this EMF is going to be non-conservative, it's going to kind of act like friction. So eddy currents like this are used for braking. So when this plate enters or leaves the magnetic field, we're going to dissipate energy through these eddy currents to slow the plate to stop. So sometimes these are desirable, right? Eddy currents are actually used in braking for various items to get them to stop quicker, more quickly. But sometimes they're not desirable. So when you don't want eddy currents, what you do is shown here all the way on the right. You either cut slots or you add a dielectric material. You laminate your conductive material and interrupt the conductor so that eddy currents can't fully develop in your conductive material. Right, and that's one way you can prevent eddy currents and design a material that's not going to have this problem if you don't want that dissipation of energy. All right, so that wraps up chapter 31 about Faraday's law. We will start with chapter 32 this week as well, so look out for those recordings also.